All right, so carrying on with gravitational potentials, we just wanted to stop and reflect a little bit about what we just learned. And the main objective is that what we have to do in this section was to understand the concept of gravitational potentials, which I tried to show in the last video. And in this video, we're going to try to calculate and apply gravitational potentials in a few different ways. And then the final thing that we're going to do is look at graphs of gravitational potentials and try to understand how we can interpret some information and draw some important points of view from it. Okay, so the formulas that we've covered so far on the left here is the universal law of gravitation, Fg equals g m1 m2 over r squared. And then I showed how we can convert that into g, which is the gravitational field strength, by dividing m2 from both sides. And then you'll get gravitational field strength, which is g times m1 over r squared. That allows me to calculate gravitational field strength at any point, very far away from the surface of a planet. And then the final thing that we looked at was calculating gravitational potential, which is the work done to move a point mass from an infinite distance away to a point in a gravitational field. And so something that you'll have to be able to do is to be comfortable at interconverting these formulas on your own. They're all in your data booklet, but you should be able to see exactly how you can easily interconvert. How would you be able to go from gravitational field strength, G, in the middle? How would you be able to go from that and calculate the force? Well, the formulas themselves tell you what you need to do. G times the mass of an object will give you the force of gravity. On the other hand, how would I go from gravitational potential all the way to gravitational force? You can see that these formulas can be interconverted. And that's something that they often ask you to show on an exam, or you have to actually apply that information from words, okay? All right, so the first topic that we're going to cover right now is how to calculate gravitational potential in complex systems, okay? It's pretty easy for us to go and just calculate imagine the moon wasn't there, for me to go calculate what is the gravitational potential due to the Earth at this little point. We found that using the formula Vg is equal to Gm over r. That formula would allow me to calculate the gravitational potential at a point. But what happens if we are placed at a point exactly in the middle between the moon and the Earth? What would the gravitational potential be? The moon is pulling me towards it. The Earth is pulling me towards it. So I wonder, would the gravitational potential be smaller or would it be greater? That's something to think about. And we talked about it at the end of the last little video. I kind of rushed it there because I was getting into a little bit more information than I should have at that point. But how would I calculate exactly what the gravitational potential, that is the work to bring a mass from an infinite distance away, to bring it to that point? That's what the definition of gravitational potential is. The work per unit mass to bring an object from an infinite distance away to that point right in the middle over there, okay? So how would I be able to calculate that? And more importantly, is it going to be less or is it going to be more? Well, work is scalar, like I said in the video. So the work that's going to be done is going to be influenced by two different objects. It's actually going to be a lot larger than if it was just the Earth on its own. Both the force of gravity from the moon and the force of gravity from the Earth are going to influence that object, and they're going to pull it in even stronger. So there'll be more work per unit mass to put that object there. Okay, does that make sense? And that work would actually be more negative. All right, so one way to be able to calculate this, pretty simple. Okay, let's call this, oops, it keeps on switching to the eraser. R1, R2, let's call those distances R1 and R2. Okay, in order for me to calculate the gravitational potential, I would just basically have to treat them on their own. So what is the gravitational potential here? That's due to the Earth. Okay, and this is going to be the mass of the Earth. And this, on the right-hand side, is going to be the gravitational potential due to the moon, which is going to be G, the mass of the moon, divided by R2, this was R1. Okay, and to find out the total gravitational potential at this point, right over here, it's going to be the gravitational potential at that point is going to be equal to Vg due to the Earth plus Vg due to the moon. So they're additive. Okay, so the gravitational potential there is going to be influenced by both the gravity of the moon and the gravity of Earth, and it's going to be large. The gravitational potential energy of that object will be larger due to the fact that there's two point masses there. And one way I can think about that is that conceptual well approach. Okay, if I just have a well due to the Earth, but then I add a well due to the moon, what's going to happen is that curvature in space is going to get deeper because there's two objects inside. Okay, sorry, this doesn't work out that well. Okay, there's going to be two objects inside. I'm just trying to make that. Here's the moon, here's the Earth. And what I've done is I've effectively made that space deeper because I added two objects into that well. Okay, the sides of that well are going to become steeper. Okay, meaning that the gravitational field strength, or the work that you'd have to do to take that object out, is going to be greater. Okay, so if I placed an object there, so that's something important. So to go back and summarize, when you're calculating the gravitational potential in a complex system where you have more than one object of mass, you got to use the formulas that we have already showed to calculate gravitational potential, and you have to treat each object separate. You'd calculate the gravitational potential due to each object, for example, the Earth, and the gravitational potential due to the moon, and then you would add them together. And remember that gravitational potential is negative. I forgot these negative signs. Okay, so the sum would be a very large negative number. Okay? All right. So another concept that we need to think about is gravitational potentials as drawn as those concentric circles. Remember, I drew an object in space, such as the Earth, and we're trying to take a look at what does the gravitational potential look like at different points, and I drew them as concentric circles, if you remember. So each of these concentric circles is a different gravitational potential. Why? Because the radius from the center of the Earth is fixed and it goes around in a circle. Okay, the radius, the other one is larger. Okay, the greater the mass, if I have a very large object, the spacing between gravitational potentials is going to get a lot smaller. Okay, if I have a smaller object, the spacing between let's say that these gravitational potentials are going up by a factor of 100. Let's say that this is 200 and now this is 100. Okay, if this was a heavier object, this was a much heavier object, 200 and 100 would be a lot closer together. Okay, because the whole well got steeper. Okay, so you'll see diagrams that'll ask you what'll happen to the spacing between two different potentials if I make the mass a lot larger. Well, they're going to get closer and closer together. All right, so that's just because the force of gravity is going to become a lot stronger. So the smaller distances are going to add up to a lot larger. It's joules per kilogram. It's going to add up to a lot larger energy. Sorry for forgetting to write the units of gravitational potential. Okay, so gravitational potentials are those concentric rings. And another way to describe how they relate to gravitational fields, okay, I'm just going to erase all this, is just to give you another perspective of how they work, those concentric rings. If I drew an object, okay, such as the Earth, and then I drew the gravitational field around it, okay. Now remember, the gravitational field strength is going to be the same when the spacing between these lines are the same. So as I make a concentric ring that has a fixed radius, you can imagine that the spacing, if I drew that accordingly, you can imagine that the spacing is going to be the same. And as I move further away, the spacing gets larger. So remember I talked about that in one of the episodes where I said that when those field lines get further and further apart, the gravitational field strength weakens. Okay, and that you can see that the gravitational potential here is going to be stronger than it is out here because the field lines are further and further apart. And I can somehow take a look at this and get an idea like I'm looking into a gravitational well, like a divot in space. Okay, if I had an object making that divot in space, you can see that those concentric rings are getting further and further apart. Okay, and the steeper that well is, the stronger the gravitational field strength is, the greater the work you're going to have to do to get out of that gravitational field strength, the stronger the gravitational potential. So these concentric rings are called equipotential surfaces. That means that anywhere along that ring, I have the same gravitational potential. Okay, the same V, Vg, anywhere along that ring. And as I change my radius, I'm going to change my gravitational potential. Okay, so what kind of calculations do I have to do with gravitational potentials? Like I described in the last episode, right? They could ask you to calculate how much work you would have to do to go from there to there, okay? And then you just have to calculate the change in gravitational potential. Once you've calculated the change in gravitational potential, the work that you would have to do would be the change in gravitational potential times mass. Okay, so you can see a lot of good examples of that in your text. Okay, now the last thing that I wanted to talk about was interpreting graphs of gravitational potential. So what would happen if we graphed how the gravitational potential changes around a planet? So here's my planet, okay, and I'm just graphing as I'm getting further and further and further and further and further away. What does that gravitational potential look like? Okay, now this surface over here, this line that you see, the curved line in the graph, that kind of looks like part of a well. Actually, imagine that there was an object at the bottom over here and looked like that. That kind of looks like the curved space. Well, actually it is, and each of these points along that line would be the change in the gravitational potential. Okay, so one thing I can take a look at is, why isn't it linear? Well, it's not linear because the formula is 1 over r, right? So Vg is equal to g m over r. So the relationship is inversely proportional. That's why it's not linear. And when I take a look at these points, other than that, when we're looking at graphs, we have to take a look at a couple things. What is the meaning of the slope? What's the meaning of the gradient? So what does the gradient mean in that graph? Well, if I took the gradient, for example, at that point, okay, I'm going to draw a tangent line to mimic the gradient. Okay, what would the gradient be here? This is delta r, that's delta Vg. So the change in gravitational potential over the change in r, what does that represent? Okay, so if I take a look at the formula, if I took Vg and I divided it by r? If I took V and I divided it by r, what does it give me? Okay, so I got to remember what V is. V is the amount of work I had to do to bring an object from infinity to a point in space per unit mass. Okay, so V is equal to work divided by mass over r. Okay, and work is equal to force times r over mass over r. Okay, I can see that the r's cancel out. What do I have left? I have force over mass, which is equal to g. Okay, so the gradient in this case of that graph is my gravitational field strength. Okay, so as I look at that gradient, I can say that the gradient at every single one of these points shows me how the gravitational field strength is changing as I move further and further out. And that's what we just talked about up here. As I move further and further out, the spacing between the gravitational field lines increases and the gravitational field strength decreases. And you can see that also in the graph, that the slope of that line is decreasing as you're going up through that graph. Okay, so that's what, just to summarize, when you're interpreting graphs of gravitational potential, a very important thing to look at, after looking at the units on the axes, if you're looking at the slope, V divided by R is the slope, V divided by R is gravitational field strength. Okay, if I was looking at other types of graph of gravitational potential energy over R, I wonder what the slope of that is. I'll let you guys try to think about that as you're going through practice problems in your text. Okay.